Welcome back to Integral Calculus. In this video, we're going to be applying the method of trigonometric substitution as our tool of choice for integrating radicals. Right. This isn't a end-all be-all, this isn't a one-size-fits-all solution, but as a general principle, whenever you're dealing with an integrand that has a fractional power in it, if a simple u substitution doesn't work, a trigonometric substitution is usually the right choice, the right second approach. So let me get my head out of the way and we will dive right in with an example. Here I have the integral of the square root of 4x squared plus 9 dx. The first thing that you want to try whenever you're dealing with something like this is a u substitution. I would try to let u be the stuff inside the radical. In this case, that would be 4x squared plus 9. And then by doing that, I get that du is going to be 8x dx. And I realize that I need to get an x in there. And if I try to get an x in there with what I have, well, x is the square root of u minus 9 over 4, and that's just going to get me right back to another radical. Right, so u substitution doesn't work. That's an important first step. Don't waste your time on trigonometric substitution if an easier method is going to work. All right, so trig substitution is my tool of choice. And when trig substitution is my tool of choice, I start by drawing a right triangle. I look at the expression. This expression involves addition. And I remember that whenever I'm dealing with addition, I generally am going to want to use a tangent. So I want tangent of theta to be equal to the variable part, I guess the square root of the variable part, right? I usually have a u squared plus a squared. So I want this to be 2x over, and then I want the square root of the constant part. The square root of 9 is 3. I said 3, I wrote 9. Right? And tangent is opposite over adjacent. So the opposite leg right here is going to be labeled as 2x. The adjacent leg down here is going to be labeled as 3. And using the Pythagorean theorem, I get that the hypotenuse is going to be the square root of 2x all squared, which is 4 times x squared, plus 3 squared, which is 9. From here, I can write that, well, the side that has my radical is the hypotenuse, my constant is the adjacent side, and hypotenuse over adjacent is secant. So secant of theta is the square root of 4x squared plus 9 all over 3. Rearranging this, I have that x is 3/2 times the tangent of theta. From there I can say that, well, dx must be 3/2 times secant squared theta d theta. Then rearranging this other expression, I have that the square root of 4x squared plus 9 is equal to 3 times the secant of theta. All right, and now it's just a substitution. Because I've got this, I've got that. This integral becomes 3 times secant of theta times 3/2 secant squared theta d theta, or 9/2 times the integral of secant cubed theta d theta. Yay. We have the integral of secant cubed. We know how this works. We can go through the whole process if we so desire. I do not so desire. I'm flipping back in my notes to where I went through that already. I don't have it memorized, but I do know where it is in my notes. All right, so my 9/2 is going to stay in front. And then I'm going to have 1/2 secant theta tangent theta plus 1/2 natural log of the absolute value of secant theta plus tangent theta plus our constant of integration, which technically should be in those parentheses, but 9/2 times an arbitrary constant is still an arbitrary constant. In this particular case, we ended up with secant and tangent. We already know that secant is the square root 4x squared plus 9 all over 3, and we already know that tangent is 2x over 3. I'm not going to do a whole lot to clean this up. I'm just going to distribute to get rid of the big parentheses. It looks like this is going to be 1/2 x square root 4x squared plus 9 for that first term. And then 9/4 times the natural log of the absolute value of 2x plus the square root of 4x squared plus 9 all over 3 plus c. And then the last thing I want to mention on this one, if you got here, I would be very happy. But that all over 3 is technically dividing by a constant. And dividing by a constant inside of a natural log is the same thing as subtracting a constant natural log, which can get absorbed into the plus c. This is one of those annoying tricks of logarithms that make you think you're crazy when you're trying to check your work. So if you were looking at this as a problem in a textbook and you checked your answer in the back of the book, that's more likely what they would have. Why do they do this to us? I wish I knew, but I know that it is a thing that they want to do, and I know that we can adapt to it. All right, moving onward. How about dx over x squared minus 25 to the 3/2 power? The first key thing here, this is a radical, right? The 3/2 power up here. This is dx over the square root of x squared minus 25, the whole thing cubed. And seeing that is very important to realizing what we want to do. Again, you could try a use substitution. Again, it's not going to work. So we're going to be left with trig substitution. When we're doing trig substitution, we are going to draw a right triangle. We've got x squared minus 25. variable minus constant. And the construction of variable minus constant was the one that we said shows up with secant. So I know I'm going to want secant of theta to be equal to the square root of x squared, which is x, over the square root of 25, which is 5. And secant is hypotenuse over adjacent. So I'm going to set x here as my hypotenuse. I'm going to set 5 here as my adjacent leg. And using the Pythagorean theorem, I know that the remaining leg is going to be the square root of x squared minus 25, which is exactly what we were hoping for, given our expression. All right. Rearranging these formulas a little bit, I get that x is equal to 5 times the secant of theta, which means that dx is equal to 5 times secant theta tangent theta d theta. And I get that the square root of x squared minus 25 is equal to 5 times tangent theta, which means that the square root of x squared minus 25, why can't I write the number 25 today? X squared minus 25, the whole thing cubed, is going to be 125 times tangent cubed of theta. All right, and we can just plug those things in. I have 5 times secant theta times tangent theta d theta all over 125 times tangent cubed theta. And we're trying to integrate this. I've got some common factors of tangent that are going away. Although I don't quite see where it's going to go from there. I've got secant theta d theta over 25 tangent squared theta. That falls outside of all of the rules that I know. So when all else fails, I tend to fall back to, can we rewrite this in terms of sines and cosines? So I'll take the 1 over 25 out front. Secant is 1 over cosine, and tangent is sine over cosine. And that actually helps. If I multiply numerator and denominator by cosine squared, I get cosine theta d theta over sine squared theta. I can do something with that. This works out really nicely if I let u equal sine theta, then du is cosine theta d theta, and this integral turns into 1 over 25 times the integral of du over u squared. And that's just minus 1 over u. Right, so negative 1 over 25 times 1 over sine theta plus our constant. I don't have sine theta written down already, but I can go back to my triangle. Sine is opposite over hypotenuse. Here's my opposite, here's my hypotenuse. So it's going to be root x squared minus 25 all over x. And then the reciprocal of that gives us this lovely expression. So yeah, setting it up using secants and tangents was definitely the easiest way to set it up, but as soon as we got to the integral, I don't quite see what to do with that. So coming up with something else to do was definitely the right way forward, right? Sines and cosines as a substitution tool, and then having to go back to the original triangle to figure out what sine of theta is. You might have noticed at this point you could rewrite that as cosecant. It would have, I guess, technically saved a step here, but it doesn't really change anything, so I took the lazy approach and didn't bother with it. Let's wrap up with one for you to try on your own. How about the integral of x cubed dx over the square root of 16 minus x squared? Right, take a couple of minutes, see if you can figure out how to approach that one. Which trig substitution is going to be most useful? Is it obvious that it needs a trig substitution? And I'll see you in the next video.